The ocean is quiet, but not empty. Long before whales ever surfaced for air, something vast moves beneath the waves. A body longer than a bus slices through prehistoric water with almost no effort. Its skin reflects no scales, no armor, only speed and efficiency. The surface world is still healing from Earth's greatest mass extinction, yet here, life has already rebuilt itself into giants. The animal does not crawl. It does not walk. It swims with a motion so refined it will one day be mistaken for a mammal's design. Its jaws open, not in violence, but in certainty. This is a creature shaped entirely by water. Today, we're diving into how giant prehistoric ichthyosaurs, marine reptiles that rivaled modern blue whales, rose rapidly after catastrophe, dominated ancient oceans, and revealed how evolution repeatedly discovers the same solutions when life is pushed to its limits. This is not speculation. Their bones remain, locked in stone, still measuring the scale of a world long gone. Ichthyosaurs were not imagined from fragments or guesses. They are known from articulated skeletons, bones preserved in life position, stretched across rock as if frozen mid-swim. These fossils allow scientists to measure length, estimate mass, and reconstruct entire bodies with confidence. In Nevada's ancient seabeds, skeletons of Ichtyosaurus reveal animals exceeding 20 meters in length. In the United Kingdom, massive fossil limb bones and jaw fragments led to the identification of Ichthyotitan, an ichthyosaur so large that its size approaches the largest animals ever to exist. These are not isolated finds. Similar remains appear across Europe, North America, and Asia, all dating to the Mesozoic era. What makes these discoveries extraordinary is not just size, but timing. Many of the largest ichthyosaurs appear in the Triassic period. Only a few million years after the Permian extinction erased nearly all marine life. Evolution did not proceed slowly here, it accelerated. Paleontologists confirm size using comparative anatomy. Bone proportions scale predictably in aquatic animals. Vertebrae diameter, limb thickness, and skull length correlate directly with body mass. When these measurements are applied to ichthyosaur fossils, the results consistently indicate whale-sized animals. These giants are not exaggerations of smaller forms. They are biologically coherent, structurally sound, and supported by multiple lines of evidence. The Mesozoic Ocean was a different place. Temperatures were warmer, sea levels were higher. Continental shelves flooded vast areas, creating expansive shallow seas rich in nutrients. Oxygen levels in the water were stable, and seasonal extremes were less pronounced than on land. Most importantly, water changes the rules of size. Buoyancy supports mass. Gravity becomes less restrictive. Bodies that would collapse under their own weight on land can grow larger, longer, and heavier in the ocean without structural failure. Food webs also favored gigantism. Early ichthyosaurs fed on abundant cephalopods and fish that thrived after the extinction. In a recovering ecosystem, fewer competitors meant more available energy for those able to exploit it efficiently. Large size offered advantages. Bigger animals lose heat more slowly, move more efficiently over long distances, and face fewer predators. Once gigantism appears, it reinforces itself. Survival favors those who can travel farther, eat more in a single feeding, and store energy longer. The ocean did not merely allow ichthyosaurs to grow large, it rewarded it. Ichthyosaurs were reptiles, yet their bodies resembled dolphins so closely that early fossil hunters mistook them for fish. This similarity is not coincidence. It is convergent evolution, different lineages arriving at the same solution under the same physical constraints. Their bodies were streamlined and torpedo-shaped, limbs transformed into stiff paddles. The tail developed a powerful vertical fluke. Even the spine curved downward at the tail, mirroring modern whales. These features reduce drag and maximize propulsion. Unlike whales, ichthyosaurs did not nurse their young, yet they gave birth to live offspring, an adaptation that eliminated the need to return to land. Fossils preserve embryos positioned for tail-first birth, preventing drowning. Another solution later mirrored by marine mammals. Inside, their bones were dense but optimized. Not heavy armor, but structural efficiency. Muscle attachments indicate powerful swimming strokes, not bursts of speed, but sustained cruising. Evolution did not copy whales. Whales did not exist yet. Instead, water itself imposed a design, and ichthyosaurs obeyed it. Question is, how does an animal this large survive? Not through constant aggression, but through energy economics. Many giant ichthyosaurs likely fed on soft-bodied prey such as squid-like cephalopods. These animals were abundant, nutritious, and required less energy to capture than fast, armored fish. Wide jaws and conical teeth suggest gripping rather than tearing, efficient feeding without prolonged struggle. Large size allowed long-distance foraging. A giant ichthyosaur could cruise slowly, conserving energy while covering enormous areas. When food was encountered, a single feeding could sustain it for long periods. Metabolism likely operated at a level between reptiles and mammals. Not sluggish, but not constantly burning energy either. This balance made gigantism sustainable. In the ocean, being large does not mean eating constantly. It means eating effectively. Perhaps the most striking aspect of giant ichthyosaurs is how quickly they evolved. Within a few million years of the Permian extinction, forms like Symbospondylus already reached massive sizes. This rapid evolution suggests strong selective pressure. Empty ecosystems create opportunity. With fewer competitors and abundant resources, traits that favor efficient swimming and large size spread quickly. Genetic flexibility likely played a role. Early ichthyosaurs experimented with body plans rapidly, with natural selection preserving those best suited to open water life. Evolution is often imagined as slow. The ichthyosaurs prove it can be explosively fast when conditions demand it. Despite their success, giant ichthyosaurs did not last forever. By the late Cretaceous, they were gone. The reasons remain debated. Changes in ocean chemistry, shifts in prey availability, competition with emerging marine predators, and long-term environmental instability all likely contributed. What is clear is that gigantism is fragile. It depends on stability. When ecosystems change, large animals are often the first to disappear. Their extinction was not sudden spectacle, but gradual loss, giants fading as conditions no longer favored their scale. Ichthyosaurs remind us that Earth has built giants before, and may do so again. Their bones show that extreme size is not an anomaly, but a recurring outcome when life meets water, time, and opportunity. They were not mistakes. They were not monsters. They were precise biological answers to a specific world. Much about them remains unknown. Skin texture, coloration, social behavior, sound. We reconstruct what we can, but the ocean keeps its secrets well. Standing before their fossils, one truth becomes unavoidable. The present is not the peak of life's imagination. It is only the latest version, and somewhere in stone, the ocean's giants still measure the limits of what evolution can build.